Okay, to pick up where we left off in the last lecture, we were going over body-centered cubic unit cells, sometimes called BCC for short. And as we saw in the diagram, body-centered cubic unit cell contains these atoms. So it's an eighth of an atom at each corner, plus one entire atom at the center. And remember, even though the book is using different colors for atoms in different positions in these unit cells, they're really meant to represent the same types of atoms, or the same element. They're just using different colors to sort of show you which one is in which position. So this is a little bit different from the simple cubic unit cell, where you had the atoms that were touching along the edge length of the unit cell, which made the geometry really simple and easy to figure out. In this one, you've got atoms that are touching from one corner through the middle of the body of the cube over to the opposite corner. And that distance would be 4r, 4 times the radius of each sphere. And when you work out all of the geometry, you end up with an edge length being 4r over the square root of 3, which is about 1.3, what is it? It's about 2.31 times the radius of each sphere. So the edge length is 4r over the square root of 3, or approximately 2.31 r. The total number of atoms inside a body-centered cubic unit cell would be 1/8 of an atom per corner times 8 corners. So that's a total of 1 atom for the corner positions. Plus you have the 1 atom that is located at the center of the body of the unit cell. And that is another atom. So there's a total of 2 atoms inside a body-centered cubic unit cell. So that means more efficient packing than you have in the simple cubic unit cell. And you can actually also see that if you figure out the packing efficiency, it turns out to be 68% as opposed to 52% for the simple cubic unit cell. And the coordination number in this case for a body-centered cubic unit cell is 8. That is, each sphere is in close contact with 8 other spheres, as opposed to the simple cubic unit cell where the coordination number was only 6. And so the higher the packing efficiency or the higher the coordination number, the more atoms you have within the unit cell, and the more stable the more stable it tends to be, and the lower the potential energy tends to be. Again, you can calculate the packing efficiency of a body-centered cubic unit cell, even if you don't know what the atoms are that make it up. You don't actually have to know the radius, because once again, the radius ends up canceling out. The packing efficiency, as we saw with the cubic or simple cubic unit cell, is the volume of the atoms over the volume of the cube, or the volume of the unit cell times 100. Well, we have here the volume of the atoms would be 4/3 pi r cubed for each atom, and there are 2 atoms inside the unit cell, and the volume of the cube is going to be edge length to the 3rd power. And we can work this out a little bit. Let's see, this would be 8/3 pi r cubed. And in the bottom, this would be 64 r cubed over this 3 times the square root of 3 on the bottom. R cubed cancels out, and you end up with just numbers. So it doesn't matter what the radius is. 8/3 pi, you can do that on your calculator. It's about 8.378. And 64 over 3 times the square root of 3 is 12.32 approximately. Multiply that by 100 and you get 68%. 68.0 in fact. So it works out, and again, you don't even have to know what the atom is in order to figure that out. That leaves us with the other main type of cubic unit cell, and that's the face-centered cubic unit cell. Okay, face-centered cubic is similar to body-centered cubic, except that the extra atoms are centered at each face of the cube instead of at the center of the body of the cube. This is sometimes called FCC for short, face-centered cubic. So it's also similar to simple cubic, but with an atom centered at the center of each face of the cube. Each of those, the face-centered atoms, belong to 2 unit cells. And we can see on, let's see, atoms in this case are touching along the diagonal of each face. And so that diagonal would be equal to 4r, 4 times the radius. Face-centered cubic would be at the bottom of page 493. Here's a way of representing it where you have, excuse me just a moment. Okay, here's an example where you have purple for the corner atoms and sort of that golden color, if you want to call it that, for the face-centered atoms. And here is what is within any one particular unit cell. You see you've got 1/8 of an atom at each corner, and you've got 1/2 an atom at the center of each face. The atoms are touching along the diagonal of each face, and the diagonal length for each face would be 4 times the radius of the spheres, because there's one radius there, here's another one, here's a third one, and here's the fourth one. So the face diagonal is 4r, and from that you can figure out what the edge lengths are using the Pythagorean theorem. And it turns out the edge length is equal to 2 times the square root of 2r. The total number of atoms within a face-centered cubic unit cell is going to be 1/8 of an atom per corner times 8 corners, and that's 1 atom, plus now we've got 1/2 of an atom within any given unit cell on each face, and a cube has 6 faces. You know, left, right, top, bottom, front, back, for a total of 6. And 6 times 1/2 is 3. So that actually makes for 4 atoms total in a face-centered cubic unit cell. And so that has pretty good packing efficiency when it comes right down to it. The packing efficiency is better than any of the ones we've seen so far, although maybe not quite as much better as you might expect. It's 74%, and the coordination number is 12. So each sphere is in close contact with 12 other spheres. Again, you can calculate the packing efficiency just by having the volume of the atoms, total volume of all of the atoms in the unit cell, divided by the volume of the cell, or the volume of the cube in this case, because it's a cube. And let's see, the volume of the atoms. Each atom is going to have a volume of 4/3 pi r cubed. And there are 4 of them, so it's 4 times 4/3 pi r cubed. And the edge length, as we said, is 2 times the square root of 2 times r. And edge length to the third is the volume of a cube. And so we have 16/3 pi r cubed over 2 times the square root of 2 to the third power is 22.63 r to the third. Notice that r to the third cancels out, so it doesn't matter what the radius is. And we end up with 16.76 over 22.63 times 100, and that is 74.0%. So there you go, 74% for face-centered cubic. Some of the other things that you can do with knowing the unit cells and the packing efficiency and things like that would be, say, calculating densities for various metals, possibly, or various substances, not just metals, and perhaps even identifying the substance based on its density, or figuring out its molecular weight by figuring out, say, the total mass of atoms within the cell, and then divide that by the number of atoms in the cell, finding out the mass per atom. And then you can multiply by Avogadro's number to find the mass of a mole of the substance and compare it to the periodic table. And that way you can figure out what it is. So an example would be, say, to calculate the density from atom size and unit cell type. Chromium, turns out, has a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. And so our mission is to calculate the density of chromium in grams per cubic centimeter. Well, what we need here for density is mass and volume. But we have to sort of keep in mind how these atoms are arranged. They're arranged in a certain pattern, in this case a body-centered cubic unit cell, which has some empty space between the atoms. So that's the way that chromium atoms arrange. And so anytime you have a sample of chromium, it has those empty spaces between the atoms. So you have to include those empty spaces in the volume, even though they don't contribute to the mass. And so what we need is the mass of chromium atoms and the volume of the unit cell, not just the volume of the atoms. So the mass will be the mass of the atoms, and the volume will be the volume of the unit cell. Although actually, technically the mass is also the mass of the unit cell, because all those empty spaces between the atoms don't contribute anything to the mass. So the mass of the atoms actually is the mass of the unit cell. But what we really need to make sure is that we're getting the volume of the entire unit cell, not just the volume of the atoms. Okay, so for that, what we need is to know, first of all, how many atoms are in each unit cell. For body, sorry, body-centered cubic, that's 2. And we can then find the mass of 1 atom of chromium by looking at the periodic table, which tells us that there's 52 grams of chromium for every mole of chromium. And we know how many atoms are in a mole. There's 1 mole of chromium for every 6.022 times 10 to the 23rd atoms. So moles of chromium cancel, and we get grams per atom. And that is 8.635 times 10 to the minus 23 grams for 1 atom. That's 1 atom. The unit cell contains 2 atoms, so the mass of chromium in the unit cell is 8.635 times 10 to the minus 23 grams of chromium per atom. Times 2 atoms of chromium in the unit cell, and we get 1.727 times 10 to the minus 22 grams of chromium that are in the unit cell. So there's our mass of the unit cell. Now what we need is the volume of the unit cell. So volume of the cube is edge length to the 3rd power. Edge length for body-centered cubic unit cells is 4 times the radius over the square root of 3. And the radius is 125 picometers. And to get that in centimeters, you're going to want to change picometers first to meters. So there's 1 meter for every 10 to the 12th, 10 to the 12th picometers. Okay, so picometers cancel. You'd have it in meters now, but we want it centimeters. So there's 100 centimeters per meter, and now we have it in centimeters. And in centimeters, it's 1.25 times 10 to the 8th. Yeah, minus 8, sorry. Minus 8 centimeters. Okay, so edge length is going to be 4 times 1.25 times 10 to the minus 8 centimeters over the square root of 3. And that is 2.89 times 10 to the minus 8 centimeters for the edge length. Volume is L to the 3rd, which is going to be 2.89 times 10 to the minus 8 centimeters to the 3rd. And when you work that out, it is 2.406 times 10 to the minus 23 cubic centimeters. And there's your volume. Density is mass of the unit cell divided by the volume of the unit cell. That's 1.727 times 10 to the minus 20 grams divided by 2.406 times 10 to the minus 23 cubic centimeters. And when you work that all out, you get 7.178 grams per cubic centimeter. And let's see, I guess we used 4 here, so it looks like we can use 4 significant figures. Well, actually, I had it down to 3 here, but we'll call it 4 anyway. 7.178 grams per cubic centimeter. I didn't actually look up the density of chromium, but that sounds about right. It certainly should be something close to that. And so there you go. So you just need to find the volume, or basically the mass of the unit cell, which is the mass of the atoms in the unit cell, and the volume of the unit cell, which is edge length to the 3rd power. And divide one by the other, and you've got the density. Okay, that's the cubic unit cells. Those are the simple ones. Now for the fun part. There are other unit cells that are not cubic, and they are known as closest packed structures. The cubic unit cells can get pretty good when it comes to percent occupancy, percent of the space that's actually occupied by atoms, as high as 74%. But actually, you can do even better than that if you use arrangements that are not cubic. And those are known as the closest packed structures. This has to do with how atoms stack in layers. There are a couple different ways that atoms can stack in layers. Several different, actually. A simple cubic unit cell has atoms directly stacked atop each other. So layers, basically a simple cubic unit cell consists of layers of spheres, each of them directly on top of a layer or of an atom in the layer beneath. So basically, it's atoms directly on top of other atoms. And as we've seen, this is not a very efficient way to pack atoms together. There's a lot of empty space. Only 52% packing efficiency. Even the better cubic structures like face-centered cubic, where you have 74% packing efficiency, we could still do better than that. Because, well, first of all, it's more efficient to stack the second layer in the depressions between spheres in the first layer. and so on and so on and so on as you go up. Because that's the way that you can get spheres as close to each other as possible. Don't stack them directly on top of one another. Stack them in the depression between the spheres in the lower, in the next layer down. And on page 495, we have a sort of a representation of that under the closest packed structure. So we're looking at something like this, and then basically in the next layer up, you would put a sphere here in the depression between these three atoms, and you'd put a sphere here and here and here and here in all these depressions between the layer below. And that gets them closer together than you would be able to get them otherwise. In other words, you want the spheres to be offset in alternating rows by half a sphere. But then the next question is, where should the third layer go? Because there are a couple different ways you could do it. The third layer could go directly over the first layer. Or in new positions that don't have atoms directly under them. They're going to go into depressions between the atoms in the second layer, but should they go into the depressions that are directly above atoms 2 layers down? Or should they go in depressions that are not over atoms 2 layers down? And actually, both ways you get the same coordination number and the same packing efficiency, but those are 2 different arrangements that have 2 different names. So if the third layer is directly above the first, that's known as hexagonal close packing. And the abbreviation ABA is often used, with A and B representing the positions of the atoms in the first and second row. And then the A at the end just tells you that the atoms in the third layer are in the same positions as the atoms in the first layer, or in other words, directly above them. So ABA means hexagonal close packing. And let's see, hexagonal close packing on page 496 is basically this arrangement here, where you have the first layer with the atoms positioned like so, and we call that the A positions. And then in the second layer, you position the atoms so that these atoms fit into 2 depressions between the atoms in the B layer. And then the third layer, you put atoms into depressions in the B layer that happen to be directly above the positions where the atoms were in the first layer. And so you have A, B, A. And that continues throughout the entire structure as you go along. A, B, A, B, A, B, all the way up. Okay, so this would be A, B, A, and then B, and then A, and B, and so on. A, B, A, B, A, B, on and on and on. The coordination number in this case would be 12. which is 6 atoms. Each atom will be in close contact with 6 atoms in the same layer, plus 3 atoms in the layer above and 3 atoms in the layer below. And again, you can see that here on page 496, because if you pick this atom in the center here to find out how many nearest neighbors that has, well, it's got 1, 2, 3, 4, 5, 6 in the same layer, plus it's got these 3 above that are in direct contact with it, and these 3 in the layer below that are in direct contact with it. So that's a total of 12. And the unit cell is hexagonal in shape. The interesting case is the other case. If the third layer spheres go into new positions, positions that are not directly over anything in the first 2 layers, then what you have is cubic close packing. And this is known as CCP. Actually, hexagonal close packing is known as HCP. And the pattern here, instead of AB, 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 it would be ABC, ABC, and so on. The coordination number here is also 12, because it's also, each sphere will be touching 6 other spheres in the same layer, plus 3 atoms above and 3 atoms below, so it's still 12. Only the atoms below that sphere will be arranged differently from the atoms above it. And so that's what you see down here at the bottom of page 496. Again, if we choose this atom right here in the very center to be the atom that we're counting the nearest neighbors for, you get 1, 2, 3, 4, 5, 6 nearest neighbors in the same layer, plus the 3 above, plus the 3 below. It's just, you'll notice that the layer below and the layer above are arranged differently. The atoms in the third layer are not directly above the atoms in the first layer. And so that's why we call it ABC instead of ABA. Interesting thing, though, it turns out that when you figure out what the unit cell is for a cubic close packed arrangement, it's face-centered cubic. Which we've seen before. Because if you remember, the face-centered cubic had a coordination number of 12. And it really does have a pretty good packing efficiency. So that's face-centered cubic again. And again, they show you on at the top of 497 how the atoms arrange themselves in the layers. And indeed, when you look at this and imagine all of these spheres being the same color, that is face-centered cubic. And so that's a face-centered cubic unit cell. Okay, so for and that's just sort of a quick overview of unit cells. We're not going to go into a lot of detail on that. We don't have time, for one thing. The next section is a look at crystalline solids overall. Particularly the different types of crystalline solids and what they're made up of. We have molecular, ionic, and atomic, based on what's found at the lattice points. So guess what's found at the lattice points? If it's a molecular crystalline solid, then it's entire molecules that are found at each lattice point. If it's an ionic crystalline solid, then ions would be found at each lattice point. And if it's an atomic crystalline solid, then of course atoms would be found at each lattice point. There are some characteristics of the three of them that are of interest. So we can look at the world of crystalline solids, and some of those would be molecular solids. Some of them would be ionic solids. And others would be atomic solids. And so these are the three major types of crystalline solids. For molecular solids, they're made up of molecules, duh. And they have low melting points, relatively speaking. And a good example of a molecular crystalline solid would be ice, which does indeed have a fairly low melting point. Ionic solids are made up of ions, obviously. So cations and anions. They have high melting points. And a good example of a crystalline ionic solid would be sodium chloride. Sodium chloride solid has a very high melting point, actually. And before we go on to the atomic solids, I notice we're well past 30 minutes. So I want to cut this segment of the video here, and we'll go on and pick up in part B.